The material in chapter 13 may be new to you. Now, I'm going to move things along since this is going on YouTube, but come to the lecture Zoom where I can spend more time with things. So there's a natural tendency for anything to mix, and that is disorder, and it's described by the thermodynamic symbol S, which is entropy. We'll talk about in chapter 9. Back in 1210, we talked about gases and how they mix spontaneously to form homogeneous solutions. Well, ionic solids dissolving in water, it's a little more complicated. So in our 13.0, I showed the sodium chloride. There are the water molecules moving in, and there are the ions being surrounded by water molecules. Do you need to review your intermolecular forces? I'm going to leave that up to you. There are homework problems that you can jump into in order to see what's going on. And in Lecture Zoom, I'll talk about this 1210 final exam question, boiling point of CH3F versus CH3L. Intermolecular forces, they affect aqueous solution solubility. So the last child reviewed what it was, but what needs to happen for a solution to form? Well, the solute-solute, those attractions must be overcome. The solvent-solvent, those attractions must be overcome. And now we have something new that has to take place, solute-solvent attractions. So what you will do is assign forces to do predictions. Will there be exceptions? Almost definitely yes. But you can put them into a couple of categories. We have our polar, we have our non-polar, and then I'll let you think about what's happening in this situation, okay? This is going to be an energy diagram, and it's going to be defined by the enthalpy of solution, where we have an enthalpy of solute, the energy we need to separate the solute, the enthalpy of solvent, the energy we need to separate the solvent, and then the enthalpy of mixing. And that's going to be the energy gained by having these attractions due to mixing. So the first two, the solute and the solvent, are always positive. We've got to put energy in. It's an endothermic reaction. I'm going to draw some pictures, but I want to tell you for aqueous solutions, that delta H solvent is going to be negligible. And I want to point out too that the mixing, the third term, it's always going to be negative. Energy is always given off in an exothermic reaction. So delta H solute, that first term, it is related to the lattice energy from Chemistry 1210. And as you recall, it's the energy needed to separate a mole of an ionic compound into its gaseous ions. The smaller the delta H of solute, the more readily the solution occurs. Hint, hint, midterm question, okay? In terms of that delta H of solution, it can be positive or it can be negative. You'll be doing some homework problems to kind of ferret that thing out, but you can see magnesium sulfate is an exo reaction, ammonium nitrate is an endo, and I'll show some of our demo YouTube videos in order to reinforce that. Your textbook has this very, very complicated picture. You can work with this one, or what I'm going to say is, here's the ones I've been using for years. If we have an exothermic reaction, we have our solid that we're putting in water. It's going to form a solution, and the delta H, I guess I should have drawn the arrow in that direction, it is giving off energy. So what has to happen? Well, there's a delta H1, which is the separation of the solute. There's a delta H2, which is a separation of the solvent. So here we have our solute, here we have our solvent, and then there's the delta H3, which is called mixing. And notice we have an endo, and an exo. All right, that's for an exothermic reaction. The delta H is less than 0. If I have an endothermic reaction, here is my solid right over here. It would be my NH4NO3. I would be putting it into water, and I would get my solution, and it is an endothermic process. Again, slower during lecture Zoom, but our separation of our solute, delta H1, our separation of our solvent, delta H2, and then as usual, our delta H3 of mixing will be an exothermic reaction, okay? So what are you going to be expected to do? Well, I'm going to show you right here. Let's say I want to dissolve Ki. They say the delta H of solution is positive. That tells me it is an endothermic reaction. So if I draw a line for Ki plus water, and they say it is a delta H positive, here is my solution. There is my delta H of solution. Here is energy on the y-axis. And again, I have a good feeling people have not seen something like this before. So it's going to take a little bit of practice. You got to do it. All right. So here is our delta H1, which is our solute-solute interaction. We know it has to be endothermic. It says the lattice energy, which is the delta H1, the solute-solute, it is greater than the energy of hydration. And so energy of hydration, that is my delta H3. That is my mixing. It is also called the solute solvent, or as you've seen me call it here, hydration. Like I said, things in this class are not going to be as simple as they were in 1210. What about the separation of the solvent? Well, this is an aqueous solution. Delta H2, which refers to the solvent, is very, very small. Sometimes they give these things numbers, all right? So if I go to my next slide, here it says, what is the hydration energy for a solid with a delta H solution of minus 50? It tells me it is exo. And it has a lattice energy of 100. That is my delta H1. So here I have my solid. Here I have my solution. And the line between this has a 50 kilojoule measurement. My lattice energy, it's going to be 100 kilojoules. Remember I said that the aqueous solution, very, very tiny. So what they want to know is they want to know what is the delta H3? What is the hydration energy? Well, mathematically, that line is 100 plus 50 to make 150 kilojoules. But since it is hydration, since it is solute solvent, since it is mixing, it has to be negative. So the correct answer on an exam would be minus 150 kilojoules. Again, come to lecture Zoom for all of this much slower. Something else to talk about here is you need to distinguish between processes that form solutions. There are physical processes where we get the solute back unchanged. +1, -1, +1, -1 if the water evaporates. Contrast that to a chemical process. How do I know what happened? Nickel has an oxidation state of 0, +1, -1 for HCl. Nickel chloride is a +2 for nickel, -1 for chlorine. Hydrogen is a 0. We've had hydrogen go from a +1 to a 0. Nickel go from a 0 to a +2, oxidized and reduced. Again, chemistry 1210. There's also something called a hydrate, where if you open up the solids container, water can go into the lattice. And you need to include this in your molecular weight. What do I have here? Some real life examples. Anybody who's been in the guard or in the service, MREs, meals ready to eat. One time a student gave me one. You break a packet and it heats up and it gets really, really hot and it cooks it is what it does. That is one that is an exo process. They thought you could sell coffee in a can in a vending machine, but too many people got burnt. Not a good idea. Someone else said, hey, let's have some cold water at Disney World called tempura. I don't know if that really took off. But the one that you may know about is when you have an injury. Sometimes someone will give you a cold pack, or let's say you go to a football game, which didn't exist this fall, but you would take a hot pack. Yes, very fast. Come to lecture Zoom. A lot more enjoyable than this video.